Stars produce massive amounts of heat and light over billions of years. But that takes huge quantities of fuel. Until the early 20th century, no one had any idea what this fuel was.
The greatest problem facing physics at the turn of the last century was what drives the energy of stars. All you had to do was look outside and realize there was a huge gaping hole in our understanding. To solve the secret of the stars, we needed a new engine. We needed a fabulous source of energy that could drive a star for billions of years at a time.
And it took a genius to discover it. Albert Einstein. His theories proved that stars could tap into the energy inside atoms.
The secret of the stars is Einstein's equation E equals mc squared. In some sense, matter, which makes up our body, is concentrated energy, condensed energy, energy that has condensed into the atoms that make up our universe.
Einstein showed that it's possible to release this energy by smashing atoms together. It's called fusion, the same force that powers stars.
It's astonishing to realize that the physics of the very small subatomic particle physics determines the structure and nature of stars.
From Einstein's theories, we learned how to release the energy inside an atom. Now, science is trying to simulate a star's energy source to control the power of fusion in a lab. Inside this laboratory near Oxford, England, there's a machine which every day Andy Kirk and his team transform into a star on Earth.
This machine is called a tokamak. It's effectively a large magnetic bottle, a cage to hold a very hot plasma. We're able to recreate the conditions within a star.
Inside the tokamak, hydrogen atoms naturally repel each other. To smash hydrogen atoms together, the tokamak heats them to more than 166 million degrees. At these temperatures, the energized hydrogen atoms are moving so fast they can't avoid smashing into each other.
If you heat it up, heat is motion, and the motion of hot particles will be enough to overcome the repulsive force.
When everything goes right,
Starting shot.
the result is the single best power plant in the universe, nuclear fusion. Traveling at over 1,000 kilometers a second, the hydrogen atoms smash into each other and fuse, creating a new element, helium, and a small amount of pure energy.
The hydrogen gas weighs slightly more than the helium. You lost mass in the process of burning. That mass that you lost, the missing mass, turns into energy.
The tokamak can only maintain fusion for a fraction of a second. But inside a real star, fusion continues for billions of years. The reason is simple: size.
The engine which drives a star is gravity. That's why stars are big. Stars are huge. You need that amount of gravity in order to compress the star to create fantastic amounts of heat sufficient to ignite nuclear fusion. That is the secret of the stars. That's why stars shine.
Fusion at the core of a star generates the explosive force of 1 billion nuclear bombs every second.
A star is a gigantic hydrogen bomb. So why doesn't it simply blow apart? It's because gravity is compressing the outer layers of the star.
Gravity and fusion are in an epic battle.
We have this constant tension between gravity, which wants to crush a star to smithereens, and also the energy released by the fusion process, which wants to blow the star apart. And that tension, that balancing act, creates a star.
This power struggle plays out over the entire life of a star. And these battles within the star create light. And each beam of starlight makes an epic journey. Light travels at 1,080 million kilometers an hour. A beam of light could travel around the Earth 7 times in 1 second. Nothing in the universe moves faster. Yet most stars are so far away, their light takes hundreds, thousands, millions, even billions of years to reach us. So when the Hubble Space Telescope looks into the far corners of our universe, it sees light that's been traveling for billions of years. The light we see today from Eta Carinae left that star when our ancestors first farmed the land 8,000 years ago. Light from Betelgeuse has been traveling since Columbus discovered America 500 years ago. Even light from our own sun takes 8 minutes to reach us. But even before light starts its journey through space, it's already been traveling for thousands of years.
When the sun fuses hydrogen into helium in its core, it creates a photon of light, a particle of light.
That new ray of light has a long way to go just to reach the star's surface.
There's a whole star in its way. And so when the photon is created, it doesn't get very far before it immediately slams into another atom, another proton, another neutron, something. It gets absorbed and then shot off in another direction. And so it's sort of randomly moving around inside of the sun. And it has to work its way out.
For the photons, it's a wild ride, smashing into atoms of gas billions of times as they struggle to escape from inside the star.
What's funny about this whole process is that it takes the photon thousands and thousands of years to get from the core of the sun to the surface. And yet once it hits the surface, it's only an 8-minute trip from there to here.
Photons are the source of light and heat, but they also cause something far more destructive: the solar wind. As they reach the surface, photons heat up the outer layers of the sun, sending it hurtling around the star, creating extreme turbulence and intense shock waves. It's so violent, we can actually hear it. Picked up by the orbiting SOHO satellite, this is the sound of the sun. The speeding gases also generate powerful magnetic fields. As the star rotates, the fields clash, and burst through the surface. Giant magnetic loops erupt into space. Some are so large the Earth could pass right through them, with thousands of kilometers to spare. They are spectacular, and they're deadly, blasting a stream of electrical particles deep into space. This is the solar wind. It can damage spaceships and satellites, even put astronauts' lives in jeopardy. To discover how the magnetic loops trigger the solar wind, a team of scientists at Caltech recreate the surface of a star right here on Earth.
It's very exciting to be able to create in a laboratory the same sort of physics that are on the solar surface. We can't go there, we can't even send probes there, but we can try to study what's happening there.
An airless chamber simulates the vacuum of space. An enormous electric current produces a pair of man-made magnetic loops.
The main difference between the plasma loops we make in the lab and the ones on the surface of the sun is just their size. The ones we make in lab are, about this big, and the ones on the surface of the sun can be many times the size of the Earth.
Their experiment reveals that when magnetic loops clash in the lab, they trigger a massive burst of energy. When giant loops collide on the surface of a star, the energy released sends temperatures soaring from 5,500 to 5.5 million degrees. That extreme heat triggers the solar wind, sending millions of tons of particles streaming out into space. The bigger the star, the more deadly the wind.
If we were orbiting a star like Eta Carinae at the same distance, it would be hell on Earth, quite literally. The amount of energy blasting down on the Earth would strip away our atmosphere, boil our oceans, melt the surface.
Understanding how stars work could help us protect ourselves by predicting their most destructive forces. But there's nothing we can do to protect ourselves when a star dies. In its final moments, it annihilates everything around it.